Okay, so there are 3 more problems in this exercise set, and we are supposed to be doing more for these problems. So we need to find the intervals of increase or decrease, and we need to find local max and local mean, and we need to find the intervals of concavity and the inflection points, and finally, we want to draw the graph. So we need to sketch the graph. You are also asked to track your work with a graphing device if F1. So let's start with number 44. So this is an algebraic function looking very ugly. So let's actually try to do this slowly. So to get the derivative is pretty easy. You just use the power rule. So this will be 5 times 2 over 3 times x to the, well, 2 over 3 minus 1, that will be minus 1/3. Okay, so this is the derivative of the first guy, and the derivative of the second guy is going to be equals to 2 times 5 over 3 times x to the, well, 5 over 3 minus 1, that will simply be 2 over 3. Okay, so this is the derivative of g, and we should probably organize a little bit better to actually write it as, so let me just factor out the common factor. So you see that these two guys are precisely the same, namely 10 over 3. So I can factor it out, and moreover, I can also factor out the negative powers in the front. So that way this will become something nice looking. So I will get x to the minus 1 over 3. So then the first guy becomes 1. And for the second guy over here, I will need to actually supplement. So in order to get an x to the minus 1 over 3 power, I need to plus 1 over 3. So that way I get x to the 2 over 3 plus 1 over 3 for the second guy after the factorization. But 2 over 3 plus 1 over 3 is precisely 1. So I get x to the first power. Okay, so this is the derivative. I can further rewrite it as 10 over 3x to the cube root, and then times 1 minus x. Okay, so then you see that g prime of x equals to 0 if x equals to 1, and g prime of x does not exist. This simply means the denominator equals to 0, so that means x equals to 0. So we notice that this x equals to 0 is inside the domain. It's not an endpoint because the domain for this function is in the minus infinity to plus infinity. So remember, when you are dealing with a power function whose, well, the power is going to be a rational number whose denominator is actually an odd number. So if the denominator is an odd number, so then this guy is defined everywhere. If q is odd. So if q is even, so this means, well, x to the p over q is defined. So there are 2 possible cases. So the first case is on 0 to infinity. So this happens if p over q is strictly greater than 0. Equals to 0 is fine as well. But actually equals to 0, yeah. Okay, let me actually say that this is going to be strictly greater than 0. And there are 3 cases actually. So minus infinity to infinity if p happens to be equals to 0, because in this case the function is simply constant. And the last case is actually going to be open bracket 0 to infinity. So this happens when p over q is going to be less than 0, because in this case, well, the x is supposed to be placed in the denominator, and the denominator should never be 0. All right, so in this situation over here, because the q is odd, so then the function is defined so every guy over here is defined everywhere. So that's why the domain is this guy. So in this case, x equals to 0 is a genuine critical number. So then together with the 1 over here, so this will separate, they will separate the real line into 3 parts. And we should discuss the increasing, decreasing, well, over these 3 intervals. Okay, so then let's again look at each factor. So 1 minus x is negative when x is greater than 1, and 1 minus x is positive everywhere else. Okay, so then the cube root of x is going to be positive whenever x is greater than 0, and cube root of x is going to be negative when x is less than 0. Okay, so also notice that the 10 over 3 in the front of g prime is positive, so that way all we need to look at is the product of these 2 guys. And it's pretty easy for us to determine that over here the function is decreasing because the product of these 2 factors are negative, and over here the function is increasing, And over here, the function is decreasing. Okay, so this finishes the analysis of increasing and decreasing intervals. Now let's actually find the function values. So at the point 0, g of 0 is simply going to be equals to 0. And at the point 1, g of 1 is simply going to be, okay, so 5 times 1 to the whatever power is going to be equals to 1. So, and then minus 2 times 1 to the whatever power is still going to be equals to 1. So the answer will be 3. So then for the first derivative test, we see that g of 0 equals to 0 is a local mean. And g of 1 equals to 3. This is going to be a local max. All right, so this finishes the second part. Okay, now let's look at concavity, and I would rather not use the quotient rule from here, but rather I will just start from this expression in here. So then g double prime of x. So this is simply going to be 10 over 3 times the derivative of x to the minus 1/3 minus 10 over 3 times the derivative of x to the 2/3. So I will just use this form of g prime of x and perform the computation because this is easier. So then I get 10 over 3 times minus 1 over 3 times x to the minus 4 over 3. So that will be the derivative of x to the minus 1 over 3. And for the second guy, well, I have got 10 over 3 times the derivative of x to the 2 over 3, and we have seen that before. So this will simply 2 over 3 times x to the minus 1 over 3. Okay, to simplify this expression, let me perform factorization. So obviously 10 is a common factor, and this 2 copies of 3 in the denominator will also be a common factor. And moreover, I think the most negative powers of x is going to be a common factor. So I will need to get the x to the positive 4 over 3 times x to the negative 4 over 3. So this way, well, these common factors are out. Okay, let's see what remains. What remains inside for the first guy is simply going to be -1. And what remains for the second guy is going to be 2 times the product of x to the 1/3 power with x to the 4 over 3 power. All right, so let's actually write that down more carefully. So I will get 10 divided by 3 times 3 times x to the minus 3 over 4. So that will be my, so sorry, it's 4 over 3 as the common factor. Then let's actually write that. So after this factorization, well, for the first term, what remains is simply going to -1. And the second term, -2, is going to be remained, but moreover, notice what we did over here. So we have, in order to get the x to the minus 4 over 3, I need to supplement with x to the positive 4 over 3. And these two guys will combine to x to the 4 over 3 minus 1 over 3, and the answer will be 1x. So then what I should get is simply 1 copy of x here. Okay, so this is going to my g double prime of x. I can further simplify this guy as 10 times -1 minus 2x divided by 9x to the 4 over 3 power. Okay, so as you could see, g double prime equals to 0. This implies that -1 minus 2x equals to 0. So this will further implies that x equals to -1/2. And then g double prime of x does not exist. So this tells me x equals to 0. Now let's place these two numbers on another line. So I have got -1/2, and moreover, I have got 0. So these two numbers will separate the number line into 3 parts, and we need to determine the concavity. Okay, let's first look at the sign for -1 minus 2x. So when x is greater than 0, you can simply plug in x equals to, for example, 1 to get a -1 minus 2x. If x equals to 1, this guy is going to give me -3, and -3 is less than 0. So using that number, you see that the factor is going to stay constantly negative over here. And over here, -1 minus 2x is going to be still less than 0. So, but then to the left of -1/2, well, this guy will change. So -1 minus 2x will be greater than 0 over here. Okay, so the denominator, on the other hand, because it's going to be an even power of something. So even power of anything will stay positive no matter what. Yeah, it takes 0 only when at the critical number. So only takes 0 over here. Otherwise, it's going to be positive. Okay, so that way I will be able to determine my the sign of f prime using this guys, because it's precisely going to be a positive number times this over that. So over here, we see that f double prime is negative, so the function is concave downward. The function is again going to be negative. Well, so it will concave downwards, and finally to the left, it will be concave upwards. So this way finishes the concavity test, and moreover, you see that at the point -1/2, well, the concavity changes. Okay, so we need to compute what g of -1/2 is, and this looks very complicated, but it's not really that bad. So that will be 5 times -1/2 to the 2/3 power minus 2 times -1/2 of 5/3 power. Okay, so the first thing I want to do is to take care of the sign. So for the first guy over here, I actually get 5 times 1/2 to the 2/3 because, well, the negative sign, well, to an even power is going to be gone. So that's why I have here. And for the second guy, well, the negative power, -1 to the odd power, this will factor out a negative sign. So that way I get positive 2 times 1/2 to the 5/3 power. So this is how I deal with the minus sign over here. So the trick is actually, so whenever the numerator is going of the power is even, so you can get rid of this directly. Whenever this numerator is odd, so you could simply move it out. But then this minus sign move it out will cancel out with the minus sign over here, and I will simply get a positive over here. So that's the explanation. Okay, so then I can perform factorization. I will just factor out 1/2 to the 2/3 power. So what remains inside for the first guy is going to be 5. And for the second guy, what I will get is 5/3 minus 2/3. So that will simply be 1. So what remains will simply be 2 times the first power of 1/2. So I will obtain 6 times 1/2 to the 2/3 power. And I will further factorize this guy as follows. So this will be 3 times 2 times 2 to the minus 2/3. So then this way I managed to get a nice value. So it will be 3 times cube root of 2. Okay, so that should, this is simply because I have got 1 minus 2/3 over here. The answer will be 1/3. So then 2 to the 1/3 power, this is simply going to cube root of 2. Okay, so this is g of -1/2. Okay, so from the fact that the concavity changes at -1/2, so that I get -1/2, 3 times cube root of 2. So this guy is an inflection point. Let's draw the diagram, and then let's draw the coordinate system. And then I know that 0, 1, and -1/2. So these are the special points. Okay, so at the number 0, so we have got a local minimum, but just be a little bit careful. So if you draw the local minimum like this, then there's an inconsistency because you see that, well, the function should be concave downward to the left and to the right of the 0. So if you draw it in this way, this basically means that the function is concave upward. So this does not really make sense. So the only possibility for the function to be concave downward to the left and downward to the right at the point 0. So the only possibility is that the function is going to have some cusp point at the point 0. So really, well, the diagram should look like this. Okay, so how do we can get further confirmation from looking at the number, the derivative, as x gets smaller from the right. So x gets 0 from the right. So then the denominator is going to be approaching 0 from the right, and the numerator is also going to be 1. So then we get that the f prime of x is getting close to positive infinity. So this basically means, well, f prime of x being positive infinity. So first you have got a vertical tangent, moreover it's kind of like increasing. So that's basically what's going on to the right of 0. On the other hand, to the left of 0, if x approaches 0 from the left, so then 10 divided by, well, it's 10 times 1 divided by 3 times 0 from below. So this way you see that this guy is going to be close to minus infinity, basically speaking. So, well, the function, the derivative being minus infinity, this means the function should look like this. So you have got a vertical tangent at the point 0 and moreover a cusp point. Okay, so this is how we figure out the function will have a cusp point over here. So another way to see this is simply tell this from concavity. Okay, so this is what happens near the point 0, and let's look at what happens near the point 1. So at the point 1, well, the function takes the value 3, and moreover, so it should be look like local maximum. So the function should have to look like this way. Okay, so this is consistent with the concavity over here. So because well, this is precisely how the function should look like near 1. Okay, so then let's look at the point -1/2. Okay, I don't really know much about this number. All I know is actually going to be the following, that this guy is definitely going to be greater than 3. So, well, this means the function value will be slightly greater than 3. And I will just plot it over here. And moreover, it's going to be a point with it's going to be inflection point. So this means, well, the function will be decreasing like this. The function will be decreasing like this after hitting x equals to -1/2. Okay, so we know that this is going to be inflection point. So this means after hitting this point, the function will decrease in the way that's concave downward. But beforehand, well, the function would decrease in a way that's concave upward. Okay, so this is the behavior of the function near these 3 special points. And to understand how the graph looks like, we also need to look at the far end. So for that purpose, we need to look at the limit of the function at infinity and negative infinity. So let's do some calculations. So as x gets large, so let me actually write this. So I will first write g of x equals to, well, I will just do the factorization as we did before, x to the 2/3 times 5 minus 2x. So if x gets positively large, so the first factor gets large, so x to the 2/3 gets large, but then 5 minus 2x gets negatively large. So then this way, well, positively large number times a negative large number, so that way I will be able to get the g of x. So the g of x will be negatively large. On the other hand, if x gets negatively large, so x to the 2/3 is still going to approach positive infinity, but then 5 minus 2x now is going to approach positive infinity as well. So this way I know that g of x gets positively large. All right, so this basically means to the far end, so the function should look like this and look like this. You can probably also get from this expression that the function, there's an intercept x equals to 5/2. So this will be slightly smaller than 3. Let's actually say this is going to be 5/2. So the function will cross the x-axis at this particular point, and then moreover, it will simply move further down. Okay, with this impression in mind, so we can now collect the bits. So first, because g of x approaches positive infinity as x gets negatively large, so to the left far end, so I can actually draw the function like this. So this way, the function is decreasing in a way that is concave upward. So after hitting this inflection point, the function will be decreasing in a way that is concave downwards until it hits the cusp point at 0. All right, so that's roughly how the graph looks like. Then after the point 0, it will start increasing, but still in a way that is concave downward. So then this way, we will be able to connect these 2 pieces. And finally, after hitting 1, the function will be decreasing, passing through the number 5/2 on the x-axis, then going down until negative infinity. All right, so this is basically how we managed to draw the graph. Okay, I should probably mark a little bit over here so that so to indicate that this is the number 3, and this is the number 3 times cube root of 2, and finally, yeah, let me move this guy a little bit right. So this is going to be equals to -1/2. All right, so this is basically how the graph looks like. Okay, so this is the diagram we have obtained on Desmos. So you will see that this is basically what the graph looks like Well, from this graph, it's quite easy for you to think, okay, so that the function is actually decreasing, decreasing like a linear function to the left. You really need to zoom out a lot to discover that x at the point x equals to minus 0.5. So there is an inflection point. So yeah, this looks like a line, but then from our analysis over here, it's not supposed to be a line. Okay, so then we have got a cusp point at the point 0, and we have got a local maximum at the point 1, and it passes through the x-axis at 5/2, and then decreases down to infinity. Okay, so this basically matches up with our diagram, but actually our diagram tells more because, well, from this, so we know that this looks like a line, but it's actually not. You really need to zoom, set up those decimals a little bit more carefully to see that. Indeed, this basically means we need to change the ratio between x-axis and y-axis. Now let me actually change this guy to, for example, like 20.194, and then it will be 80.194. So this way you will see, okay, so this is not really a straight line, but actually has got some curve. But still, it's quite difficult for you to detect that at this point, well, there is an inflection point. You will find that, okay, over here, so the function is clearly concave downward, but an inflection point is still quite difficult to detect over this diagram. Okay, so this is basically how, well, so graph sketching by hand actually tells you more than the graphical calculator. Now let's actually look into another example. So f of x equals to natural log of x squared plus 9. So I will do this problem in a slightly faster way. So let's first get a derivative. By the chain rule, the derivative will be 1/x squared plus 9 times the derivative of x squared plus 9, which is only 2x. So this will be 2x divided by x squared plus 9. So to get the critical number, notice that the denominator is always positive, so we don't need to worry about where the critical number where the f prime of x does not exist. So the only kind of critical number is obtained by setting f prime of x equals to 0, and this will tell me that x equals to 0. Okay, so this is the only critical number. And also notice the domain of this function is again going to be minus infinity to positive infinity because, well, whatever inside the argument of the natural log, this stays positive. X squared plus 9 has got a minimum value at 9, so this is going to be always positive. All right, so this is my domain, and x equals to 0 separates the domain into two parts, and we can analyze the increasing decreasing interval is pretty easy to analyze in this case because, well, I know that x squared plus 9 is always positive. So then I don't need to worry about sign. So this is my denominator, and the numerator 2x is going to be positive to the right, and 2x is going to be negative to the left. As a result, the function will be increasing to the right and decreasing to the left. So moreover, we see that f of 0. So f of 0 is going to be equals to natural log of 9. I won't bother to write it down, but just because this is really easy. So f of 0 equals to natural log of 9. So this is going to be a local minimum. Okay, so this finishes part A and part B as well. So, yep. So now let's do part C. So get the concavity, and this means I need to get the derivative of this fraction, and I can simply use quotient rule. So square the denominator, then denominator times the numerator prime minus numerator with denominator prime. Denominator prime is simply 2x. All right. So then the numerator of this guy is going to be 2x squared plus 9 minus 4x squared. And then I will get a nice polynomial. So namely 9 minus 2x squared divided by x squared plus 9 squared. Okay, so this guy can actually be factorized as follows. So it will be 3 minus root 2 times x. 3 plus root 2 times x. Then x squared plus 9 squared. Okay, so this is my f double prime of x. So now f double prime of x equals to 0. This means x equals to 3 divided by root 2, or x equals to minus 3 divided by root 2. So simply means these is 0 or this is 0. So, but then if you divide root 2 on both sides, you get x equals to 3 over root 2 from this factor and x equals to minus 3 over root 2 from this factor. Okay, so these are the critical number for the derivative. Okay, so, and then you know from this guy over here, so that the denominator is never 0, so f double prime always exists. So we will just skip the discussion over there. All right, so these three numbers separates the interval, the domain into three parts, 3 over root 2, and then minus 3 over root 2. Okay, so there will be three parts over here, and we will analyze the concavity. Okay, so to analyze the sign of f prime of x, and let's do it in a way that is slightly different than what we have seen before. So let's first focus on the factor 3 minus root 2 of x. So instead of solving the inequality directly, I will just look at what happens with when x gets very large. When x gets very positive, well, because I can certainly make x very positive on the right of this number. So when x gets very positive, so this guy becomes very large. So this guy becomes very negative. A very negative number plus 3 will still be a very negative number. So this way I know that this factor will be less than 0 when to the right of everything. Okay, similarly to the left of everything, so 3 minus root 2 of x. So if x gets very negative, so then this guy is going to be very positive. So minus root 2x times a very negative number, so there will be very positive number. Very positive number plus 3 will still be very positive. So that way I know that this is greater than 0. Okay, in the middle, how do I do that? Well, I will plug in x equals to 0. If x equals to 0, then 3 minus root 2 of x is simply going to be 3, and 3 is positive. So that way I know that this is going to be equals to positive number. Okay, so this is how I determine the sign without solving the inequalities. So we can simply plug in some special numbers. Okay, so this is just one factor. And for the second factor, we do the same. 3 plus root 2 of x as x gets very positive. So this will be very positive. And 3 plus root 2 of x as x gets very negative. So this guy will be very negative. And in between 3 plus root 2 of x, if x equals to 0, so this guy equals to 3, which is still positive. Okay, so this is how I analyzed the second factor. And then x squared plus 9 squared, so this is going to be positive. So I think that I probably don't want to write it out because this is really not bothering me in determining the sign over here. Okay, nevertheless, we will get the following. So so this will be negative, positive divided by positive. So this will be negative. So as a result, the function is concave downward. And over here, everything is positive. So the function is concave outwards. And over here, 1 negative, 2 positive. So then it will still be concave downward. Okay, so this finishes the concavity test. Okay, as you see that the concavity changes at these 2 points. So I need to actually figure out the function value at these 2 points. So that means I need to figure out f of 3 divided by root 2. I need to figure out the number for this, but this is simply going to be natural log of 9 plus 9 divided by 2. So this will be natural log of 9 times 3 over 2. Okay, natural log of 9 times 3 over 2, what is that thing? So I will simply write it as natural log of 27 over 2. And I will just leave it there because I don't really know how to further simplify this guy. Okay, f of negative 3 over root 2. So, okay, so this guy is actually an even function. So I can actually skip all the process because, well, plug in a negative number. So this is supposed to be the same guy over here. So this will be natural log of 27 over 2. Okay, so this way I know that minus 3 over root 2, natural log of 27 divided by 2. So this guy is an inflection point. Let me change the color to emphasize this point. Okay, so similarly, positive 3 over 2 and natural log of 27 divided by 2. So this is going to be also an inflection point. All right, so these are the analysis of concavity and increasing, decreasing. Now let's try to draw the diagram. Let me duplicate the page. So let me skip the trouble of placing all these guys onto one single diagram because it's probably, yep. That way save you some time in the test at least. Okay, so let's first draw the coordinate axis. So we have got the number 0. And we know that at the point 0, the f of 0 takes natural log of 9. Okay, natural log of 9, I know that this is going to be, I think it's going to be slightly larger than 2 because, well, e squared is going to be less than 9 squared, but e to the third power, so this is definitely going to be greater than 9. So, so that way I know that this is going to be slightly less than 2. Slightly greater than 2. So let me say that this is going to be natural log of 9. Okay, so for natural log of 27 divided by 2, I know that this is definitely going to be larger than natural log of 9. So as long as I draw it higher, it should be fine. And let me just say that these 2 points are going to be 3 over 2 and then minus 3 over 2. So I'm just picking a random scale on the x-axis and y-axis. It really doesn't matter that much. So this will, let's say this is precisely going to be natural log of 27 divided by 2. Okay, so now let's see what happens. So we see that the function will be increasing, and moreover, it will be increasing in a way that is concave upwards. It will be increasing that is concave upwards. So that's from 0 to 3 over root 2. So that's basically what we have. And after that, well, the function will keep increasing, but where will it increase? So you should notice one thing, that as x gets large, so this guy also gets large. And natural log of a large number is going to get very large. So the limit will be infinity. So, but moreover, it will be, so the function will still be increasing, but then in a way that is concave downward. So, but then it will still approach in positive infinity. Okay, so this is basically what the graph looks like. And because this is an even function, as we can observe, so the graph should be symmetric about the y-axis. So basically, you flip the graph you have drawn to the right about the y-axis. So this is what you get. Okay, so this means we are really doing a very terrible job in determining the scale. So this is probably the best thing about drawing on the iPad, that you could simply move things around very conveniently. So let me actually do this. So I can simply shift everything a little bit below. And then I can also shift everything a little bit below. Okay, and then I get rid of this part. Okay, so this will give us the picture we wish to get. Okay, so let's go back to Desmos and see what happens. Okay, so this is the graph generated by Desmos. As you could see, well, starting from 0, well, the function will start increasing in a way that is concave upwards. But after a while, it will actually get to increasing in a way that is concave downward. Okay, so it's pretty tricky for you to figure out where the inflection point exactly is. But from our calculation, the inflection point happens at the point 3 divided by root 2. Well, 3 divided by root 2 is going to be slightly larger than 2, but not so much larger. So somewhere here will be an inflection point. But however, this is probably not that easy for you to detect directly on the graphical calculator. And also, we have determined that the limit of the function will be positive infinity. But if you zoom out simply like this, you'll probably think, yeah, okay, so the graph is going to be getting flatter and flatter. So the rate of increase is going to get smaller and smaller. So you probably think, okay, there probably will be a horizontal asymptote. For example, well, it's probably going to be at 10 or somewhere. Well, I have to correct you that this is not really the case. And yes, for logarithmic functions, well, the rate of increase is going to get slower and slower. So the graph looks flatter and flatter because the rate of increase is going to be getting smaller. But the limit is still going to be infinity. So to see this, you will have to adjust the scale of x a little bit. So in this picture, the scale of x is from -10 to 10. If we let it to be like -1000 to 1000. So you will see that, well, certainly, so this y is going to be kind of hidden. So then you see that, well, originally we were expecting the a vertical horizontal asymptote at the point 10, but now for this picture, you see that, well, the graph actually grows above 10. And if you adjust a few more digits, so let's say 10,000, so then it will further increase. Well, it's going actually passing 20 over here. So if you further zoom out, so the function, yes, it's going to be looks like a flat line, but eventually it will like pass through all the positive numbers as you could act. Of course, I'm not so sure if Desmos is capable of handling like 20 digits or something, but just to make no mistakes. So for logarithmic functions, they are not supposed to have horizontal asymptotes. Okay, so this will be the comment I should provide for this problem. Okay, now let's discuss the last problem. So s of x equals to x minus sine of x. And let's do this one real quick. So s prime of x will then be 1 minus cosine of x. So this is pretty easy. So s prime of x equals to 0. So this means cosine of x equals to 1. Okay, be a little bit careful over here. The region is going to be slightly larger. So usually we deal with 0 to 2 pi, but now we are dealing with 0 to 4 pi. So within 0 to 4 pi, you should be able to find at least 3 points for the cosine function to be equals to 1. So you should get x equals to 0, 2 pi, and 4 pi. So at this 4 points, well, the cosine of x equals to 1. Okay, one important thing. This 0 and this 4 pi, so these guys are not considered to be critical numbers because, well, they sit on the endpoint of the domain. So endpoints are not considered to be critical numbers. So the only critical number we have is going to be 2 pi. Okay, but to determine the increasing decreasing, so we will still have to keep this endpoint over here. So this will be 0 and this will be 4 pi. So endpoints are still to be kept in here, but just keep in mind that this is not they are not considered to be critical numbers. And now let me mark the critical number 2 pi, which is going to be the midpoint of this interval. All right, so then this is roughly the picture, and we wish to analyze where the function is increasing or decreasing. Okay, so over these two intervals, let's look at what happens. So this is 1 minus cosine of x. You should know that 1 minus cosine of x is always going to be positive. So it's only taking 0 when at the boundary points over here. So this way we know that 1 minus cosine of x is positive. This means the function will be increasing and increasing over here. So yeah, this is simply because 1 minus cosine x is positive everywhere. So this way we know that this 2 pi over here is neither a maximum nor minimal, but still, because at this point 2 pi, the function has got a horizontal tangent, so we should still compute its value. So f of 2 pi, s of 2 pi, so this will be 2 pi minus sine of 2 pi, and the answer will simply be 2 pi because sine of 2 pi equals to 0. So then s of 2 pi equals to 2 pi is neither local max nor local min. All right, so then this is basically what we know about this critical number. And we should also take care of the endpoints as well. So we need the endpoint values to really draw the graph. So then we know that s of 0, so this is simply going to be equals to 0. So then s of 4 pi. So this is simply going to be 4 pi because sine of 4 pi is again 0. All right, so these are the special points I can obtain from the first derivative. So it will be. Moreover, you should probably know that because of this, because that the derivative also takes 0 over here. So that if you draw the diagram, if you draw the graph, then the tangent is kind of like a horizontal also on these 2 points. Okay, so let's see what happens the next. So the next part is basically going to be the concavity. So let's look at the second derivative. So the second derivative is pretty easy. So this is going to be minus of the derivative of cosine of x, which is minus sine x. So this will be positive sine of x, and s double prime of x equals to 0. Okay, so this will tell you a lot of points. S double prime of x equals to 0. This tells me that sine of x has to be equals to 0. Over 0 to 2 pi, there will be 5 points. So x equals to 0, pi, 2 pi, 3 pi, 4 pi. So there will be 5 points on here. And for convenience, let's just arrange everything on this diagram. So I will have 0, pi, and let me mark 2 pi to the side. So over here. So 2 pi, and then 3 pi, and finally 4 pi. I will have all these guys as the critical number we obtain from the second derivative. Okay, so let me mark as well the pi over here and 3 pi over here. Okay, let's look at the concavity. So you need to recall what the graph of sine of x looks like. And let me draw it in green. So just recall a little bit that sine of x over 0 to 4 pi, what does it look like? So it will pass through 0 pi and then to 2 pi and then finally again a period. So this way it tells me the sine of x over here from 0 to pi, sine of x is positive. So as a result, the function will be concave upwards. And between pi and 2 pi, so the sine of x is negative, so it's concave downward. So similarly, upwards and downward. All right, so what does that tell me? That tells me that these 3 numbers are all inflection points. So we know that sine of, so then the point pi, and look at s of pi, what is that thing? So s of pi is going to be pi minus sine of pi, which is going to be pi again. So this is an inflection point. And then pi, 2 pi, 2 pi. This will be again inflection point. And finally 3 pi, 3 pi, because sine of 3 pi is again 0, so this will be an inflection point. Okay, so this is pretty easy. So let's actually draw the diagram then. I think we can accommodate on the same page. Yes. Okay, now let's start by drawing. Okay, let me keep it here. Okay, let's start by drawing the coordinate. So I will have got, we know the function is increasing, so we can simply set this 0 as the lowest point, so we can leave more space on the upper half. And then let me mark the special points. So we have got pi, sorry, this is 0. Let's say this is pi, and this is going to be 2 pi, and this is going to be 3 pi, and this is going to be 4 pi. Okay, so yeah, I think I should probably make the graph a little bit up to scale, but okay, anyway, it's probably not that important. Let me draw like this. Okay, so let me not draw to scale, but let me just tell that. Let me just draw the y coordinates, well, in this way. So the y coordinate, let's say this is going pi, 2 pi, 3 pi, and 4 pi. So we know that the function will pass through 0, 0, pi, pi, 2 pi, 2 pi, 3 pi, 3 pi, and 4 pi, 4 pi. Okay, so these are the special points over here. Yep. Okay, I think there is still some trouble because it's really supposed to be a straight line, but then I'm not really drawing a straight line over here. Let me adjust it a little bit downward. And let me adjust these guys also a little bit downward. So that way it looks more like a straight line. All right, so then let's say that this is going by pi, this is going by 2 pi, and 3 pi, and 4 pi. prolong this a little bit. Okay, so well, this is basically the special points we are passing, and we know that the function will have got a horizontal tangent at the function will have horizontal tangent at the point 2 pi, and moreover at the point 0, and at the point pi, so the function will have a horizontal tangent. So then, well, we know that the function will increase from 0 to pi in a way that is concave up. So let me just draw it in this way. So it has horizontal tangent at 0, then it will be horizontal tangent at 0, then it will be increasing in a way that is concave up. So then at this, so at the point pi, it will be an inflection point, so that it will be increasing in a way that is concave down until it hits 2 pi. And 2 pi is again an inflection point, so this will be start increasing again in a way that is concave up. And finally, at the point 3 pi, it will just start increasing in a way that is concave down until it hits 4 pi. Okay, so roughly speaking, this is the graph we can obtain. Okay, so it's not very precise because to really get a precise graph, we also need to get the derivative at these 2 points. But yeah, we are not really asked to do that. So, and also we are not really drawing the graph at scale. So I think this is graph, yeah, it looks ugly, but probably it works for this course already. So, all right, so this is how you should deal with number 48. Now let's look at the Desmos. Okay, so this is the graph generated by Desmos. And because we are interested in the region when x is between 0 and x and the 4 times pi, so that's 4 times pi, yes. So then, so certainly the y value will be larger. So what we are interested in, let's say y is between -1 and well, the function value at that point is going to be 4 pi. So let me just make it 4 pi plus 1. Okay, so then this is basically the diagram we are supposed to get. And you see that it's just like horizontal tangent in the beginning, increases until somewhere. Now it's indeed going to be pi a little bit greater than 3.14. Then there will be inflection point. Then so it's increasing initially as in a way that's concave upwards, then increase in a way that's concave downwards until it hits the horizontal tangent at the location 2 pi. Then it will repeat these patterns forever. Okay, so that's basically the diagram. Okay, so this concludes the very long supplementary video, and I hope that this is helping you guys to understand the rest of the problems in the exercise 11 and 12. So for the next lecture, we will be focusing on graph sketching in exercise 13. So thanks to this supplementary video, we should have more time in class dealing with those problems.